All right. So here are the notes for water filtration. We're going to be building some water filters, testing those water filters, seeing how clean we can get some water. I am going to make some really disgusting water, and we're going to see how clean we can make it with some homemade water filters. So first of all, we're going to take some notes because there's a lot to do with water filtration that we're going to need as information for this lab. And first, I want to talk about how water poor the world is. Okay, the surface of our planet is covered in water, but I want to talk about that in detail because we really are pretty water poor when it comes to water that we can use. Okay, so most of the world is water poor. Most of the world is water poor because the water that they have is not potable. Okay? Because the water they have is not potable. Okay? That's a vocab word we're going to define in a minute. But first, before we do, I want to talk about places that are water rich on this planet. Okay? So most of the world is water poor. Areas that are water rich are going to include Canada and Russia. Okay, and if you think about that, it sort of makes sense because they're covered in snow. I mean, they're really northern latitudes. The North Pole has a lot of snow and ice. Okay, so snow and ice make up a lot of that water. Okay, and Brazil is another place. Now, totally different climate. They have rainforest. But Brazil also happens to be sitting on one of the world's largest aquifers. Okay, so a lot of fresh water in Brazil. Okay, and so let's define potable, and then we're going to talk about the details of how the water of our world is situated. Okay, so let's define potable right now. Okay, potable means water that is safe to drink. Water that is safe to drink. So I believe it is a federal law, but it's at the very least a local law. If there's a tap, like a spigot or a tap in a building for water to come out of, if it's not potable, it actually has to have a sign saying that it's not potable. So technically, the water that is being used to flush our toilets is potable water, unless it has a sign on it saying it's not potable. Okay, so you could drink the water that comes into the toilet if you trusted the toilet being clean. The water that comes into it is potable. Okay. Okay, now let's talk about Earth's water. We're going to make a little flow chart. I'm going to tilt this maybe so we can see my flow chart a little better. I think I can fit it in there. Okay. So first of all, Earth's water we're going to talk about Earth's water. It covers 70% of the surface of our planet. Okay? Water covers 70% of the surface of planet Earth. 70%. It's a lot. Okay? But we can't use it all. Okay? We're going to say less than 1%. Less than 1% is potable. Less than 1% is potable. Okay? We're going to find out what I mean by less than 1% in a little bit. I'm going to slide this over. We're going to do a flow chart to show you what I mean by that. Okay? Okay. So I'm going to tilt this up, make sure we can see the whole board. Okay. We're going to split Earth's water up, and I'm going to do a little demonstration that goes along with this so you can have a visual for this as well. Okay. If this is all of the water on our planet, okay, so if we shrank all the water down into a beaker this big, okay, it's 1,000 milliliters, 1 liter of water. Okay, so let's say all of the water is represented by that beaker. Okay, 97% is salt water. Okay, so we're going to make a little flow chart. It's been a while since we've done one, but 97.0% is salt water. Okay, now if you do some mental math there, that only leaves us with 3% that is freshwater. Okay. So what I'm going to do is I'm just going to show you what that looks like. 97% compared to 3%. Okay, so if I take my 1,000 milliliters, if only 3% of that is fresh water, that's going to be this much. Okay, so if you look at this, the water level didn't change very much in here. Turn this around. Still really close to that 1,000 because we have 97%. So this is all salt water. Okay, can't use it. It's in the oceans. It's in brackish areas. Okay, but this much would be fresh water. Well, that looks like a pretty decent amount if we consider all the water. Okay, so there's our fresh water. All right, well, now we're going to break that fresh water apart because it's not this simple. Okay, so out of that 3%, we're going to split that up. 2.4% out of the 3. So it's not 2.4% of 3, it's 2.4 out of the 3, which leaves only 0.6% left. 0.6% here, okay? All right, that 2.4%, most of our fresh water is frozen. Okay, so Russia, Canada, Greenland is covered with ice, Antarctica, okay, all of that frozen water. Not very accessible, okay? If it's frozen, we can do things to make it accessible, but it takes energy, it takes time, okay? So that piece, not super accessible. The other 0.6% is liquid, okay? So 0.6% of all the water on the planet is liquid and easily, well, I'm going to go ahead and take, so this is my fresh water, okay? This is all the fresh water on the planet in my demo here. I'm going to pour out. There we go. Now this much is frozen, okay? Frozen, not easy to access frozen water. This much is fresh, okay? I know that looks like a lot, but let me put it into a beaker so that we can see what it actually is. Okay, so I have a little beaker. I'm going to go ahead and pour my 0.6% into there. Okay, so here is that beaker, and I'll put it right next to this one so we can see a lot more water is frozen than fresh. It makes me kind of nervous holding this over my computer, but there we go. Okay, so now we've split it into, frozen versus liquid. Frozen versus liquid. It's all fresh. This is our fresh water. Most of it's frozen. A little bit of it is liquid. Okay? And then, 20% of our fresh water is liquid. Okay? But then we have to split this even further. So I'm going to take my 0.6% and I'm going to split that. So these two numbers are going to add up to that 0.6%. Okay? Well, 0.59997% and 0.001% 0.0003%. So when I add those together, I get that 0.6% that's liquid. This one, the little tiny one, this is potable. This one, not potable. So this is water that exists. It's fresh, it's liquid, but it's contaminated. And it would take a lot of energy and effort to clean it in order to drink it. And we do that. We clean water and we drink it after we've cleaned it. But it takes a lot of energy and effort. This is the liquid, potable portion of planet Earth's water. Very, very small. Okay? We can also treat salt water to make it drinkable. Okay, we've heard about that in the video on the world water crisis. Okay, and that is desalination. Okay, taking salt water and taking the salt out of it, which is really taking the water out of the salt water. Okay, but it's expensive. It takes a lot of energy, a lot of time. So this is why we have a crisis. We have a very small amount of water that we can use. It's not evenly distributed around our planet. There's places that have very little water. There's places that have an overabundance of water. And this is becoming a point where big cities are starting to enter a crisis mode. And that's what we watched a video about. So if you haven't seen that video, make sure you go back and watch it so you can get some of that information. Okay? All right, so now we're going to talk about what the title of the note says. We're going to talk about water filtration because this is an important thing to do in order to get some of that non-potable water to be potable. Okay, so ways to clean water. Ways to clean water. Okay, well, first method is going to be filtration. Okay, now filtration, it's a way to separate a mixture. A way to separate a mixture. Okay, that's pretty simple, but it's going to be using size as is a major way to filter, size of particles, okay? And we're going to talk about several other ways as well. But remember that separating a mixture, those are always physical changes. So filtration is a physical change because it's being used to separate a mixture, okay? All right, now let's talk about, I'm going to come back to this one and erase it. We're going to talk about some different types of filtration. Okay, so there's one way, and it's particle size filtration. That's one that I mentioned earlier. So particle size filtration. And that is what it sounds like. When you filter coffee grounds and you let the coffee pass through, the coffee is thinner, its particles, molecules are much smaller than the grounds themselves, and so the filter paper catches the things that are big and lets the things that are very small go through. Okay, so particle size filtration is what we're most familiar with. Okay, and so this is going to be like screens can do this. If you ever watched like people who panned for gold in the rivers, they would use like a screen and kind of shake it back and forth, hoping to find little gold nuggets in what they were filtering or screening. Okay, so you can use screens. Cotton balls can do this job. Whoop. Filter paper works for this purpose. Okay, other things that could be used could be like sand or dirt. If you pack, I know we're trying to clean water, right? Not make it dirty, but if you pack something like sand into a small space and then you force something through it like water, the sand is going to catch anything that's bigger than itself and prevent it from going through. So I'm going to add sand to this list, okay? But there's other things that you can use for size as well, okay? Sometimes we use like strainers in our kitchen to let the water go through, but not the pasta. So anything like that would work, okay? All right, particle size filtration. Now, another type of filtration, which is something that might be new to you, it might not, but it's activated charcoal filtration. Activated charcoal filtration. Now, we're going to talk about this one quite a bit because it's more complicated, okay? So if we were to zoom in, activated charcoal is kind of a black, dusty, powdery charcoal. If you get it on yourself, it's going to get everywhere, and it takes a long time to get off, okay? And so if you haven't experienced that yet, hopefully you will in our class so you can see what that looks like. But if you zoomed in all the way to a little tiny grain of activated charcoal, you would see pores, okay, like pores in your skin, little holes in the surface of the charcoal, okay? So there's pores, allow water in, okay? The pores allow water in, like holes in a sponge, okay? Then they get narrow. The pores allow water in, and then they get narrow. They get narrow. They get narrow, and that traps things based on size. So that's a particle size filtration, okay? Trapping larger particles. Okay, trapping larger particles. But there's another thing that happens with activated charcoal, okay? And it's called adsorption. Not absorption with a B, but adsorption with a D, okay? So I'll write that out. Make sure you get it A-D. Okay? And if we're dyslexic, it might be hard with our D's and our B's, but this is A-D, adsorption. It's a different word. It doesn't mean soak up, okay? It's similar though. Adsorption is a chemical attraction of contaminants to the charcoal. Chemical attraction of contaminants to the charcoal. So oils and some toxins are going to be attracted to the charcoal, and they stick to it, and they don't go through. Well, the water keeps going. The water is not attracted to the charcoal, which is one of the reasons why it's so hard to wash it off your skin. Okay, but it's not attracted to it, so the water will go through, but all of those contaminants will get stuck to the surface of these little tiny charcoal particles. Okay, so attraction. This makes things stick to the charcoal. Makes things stick to the charcoal, but not the water. The water goes through, okay? Now, 1 teaspoon, so a little spoon that you eat your breakfast with, 1 teaspoon of charcoal of activated charcoal, I should say. One teaspoon of activated charcoal has the surface area of a football field. One teaspoon of activated charcoal has the surface area of a football field. So if you got activated charcoal, just a little tiny scoop in your hand, you could spread that quite a ways. Okay, now you wouldn't be able to spread that to the area of a football field. But when you zoom in and you look at every single tiny little particle and you add up the surface area of the entire particle all the way around, it's going to add up to an entire football field in one little teaspoon. Okay, that's huge. That's a lot of space to attract contaminants and make them stick. And it's a lot of pores to push the water into and get the larger particles stuck because of their size. So activated charcoal is an awesome, awesome filtering tool. Okay. Okay. Now that was number one. We talked about filtering. Activated charcoal counts as a filtration. That's number one. Now I'm going to erase this top piece here and we'll talk about the other two. They're a lot shorter. Okay. So other methods. Number two, let me see which order I went in here. Reverse osmosis. Reverse osmosis. Okay. If you have taken biology, maybe you've heard the word osmosis. You might not remember what it means, but osmosis is when water goes through a membrane. Okay. If you put, you can see this really easily if you take the shell off of an egg using vinegar. You can dissolve the shell off of an egg, and there's a squishy membrane just inside that cell. And you can make water go in to that membrane, and it kind of makes the egg kind of plump up. Or if you put the egg into like a saltwater solution, water will leave the egg and go through the membrane out of the egg into the salt water to try and water down the salt water, and the egg will get really tiny. And so that membrane that's osmosis, water traveling through a membrane. Well, reverse osmosis is forcing water through a membrane, forcing water through a membrane to clean it. Okay, so those membranes only let water through. They do not let other things through. Now, water has a tendency to go to the side that has less water or has more contaminants. And we don't want it to be more contaminated. We want it to go to the clean side of the membrane. So we can push that water through the membrane. It takes energy because you can't push too hard, you'll tear the membrane. So it takes a lot of time and energy to push water to the side that it doesn't want to be on. But that's what reverse osmosis is. And you end up with really clean, pure water. And that is one of the methods being used for desalination. Okay, so forcing water through a membrane to clean it. And another way to clean water, and it depends on what you're talking about. This way will not, reverse osmosis cleans it. We're getting just water, okay? Filtration takes out a lot of big particles. Activated charcoal can grab onto chemicals that are contaminants. Okay, but some things that dissolve in water aren't attracted to that activated charcoal, and they just go through, right? And this would remove it, reverse osmosis. But the last thing is something different. This is ultraviolet light. Okay, ultraviolet light. Ultraviolet light kills bacteria. Kills bacteria and viruses. Okay, kills bacteria and viruses. So typically, if you have activated charcoal, you probably don't need ultraviolet light to clean that water because activated charcoal will trap viruses and bacteria because they're pretty big. Viruses and bacteria are really big compared to some of the things way too big to go through activated charcoal if you have your filters set up right. But if you have a freshwater source that's fairly clean, it doesn't have any chemical toxins in it, but it still has bacteria, one of the ways that you can kill them is boiling the water. Okay, that's another way we can put up here. But ultraviolet light is a really good way to kill bacteria and viruses. And that's one of the things that we use actually at the Laramie High School swimming pool is we use ultraviolet light to make sure that we're killing anything that might be in the water. Okay, so I'm just going to go ahead and add 4, boiling. Boiling, again, this kills living contaminants. Like viruses and bacteria, it kills those, but it doesn't actually clean as far as removing anything from the water. It just kills those things and leaves them in the water. So same thing with ultraviolet light. It kills them, but it doesn't take them out. So you also want to couple these two with some kind of filtration method. So that's the water filtration notes. Thanks for tuning in, and we will see you in class.